to the course Advanced Reaction Engineering. So, in this course we are discussing steady state non isothermal reactor designs. So, already have started. So, that is continuation. So, here we will discuss multiple steady state. Okay. So, multiple steady state means we have discussed or derived for a particular reactions. Let us say when a reactor CHTR you have taken and their exchange or heat exchange is there, heat either supply or remove from the systems is there. So, means heat means if it is exothermic reactions we have to take out the heat from the systems, if it is endothermic reactions then we have to supply the heat for that particular reactions. So, energy and for that material balance and energy balance equations both we have discussed in our previous class. So, now we means whenever particular reactions is there or heat exchange facilities is there. So, here when a reactions will take place means if it is exothermic heat formations is there inside of the reactors and means heat generations would be there, and at the same time so there is coolant that would be circulate outside of the reactor to maintain the temperatures. So, therefore, heat removal part is also there, means heat generation due to the reactions and heat removal by the coolant that would be supplied outside of the reactor. So, now the heat generations and heat removal that we can write in terms of GT or RT. GT is the heat generations and RT is the heat removal. Okay, that way we are writing. Now, these are the component how they are effect of these components with the feed inlet temperatures, molar flow rates, volumetric flow rate, volume of the reactors. So, means heat generations and heat removal part how they would affect if we feed inlet temperature will vary, means low or high if we do. So, means let us say 100 degree centigrade we are feeding the feed, then so what would be these components, and if we increase the feed inlet temperature let us say 200 degree centigrade, then what would be the heat generation and removal part inside of the reactors. If we change the molar flow rates means that reactant is feeding at a particular rate, let us say 10 mole per second that we are feeding for the reactions, if we change 10 to 20, 10 to 30, so then what would affect overall heat generations and heat removal part, also by changing volumetric flow rate, by changing the volume of the reactor. So, that part basically we will discuss. So, these are the material balance lines or equations for let us say this is a first order reactions we have considered, A is going to be that first order reactions, and this is the material balance lines that we have discussed for irreversible reactions from starting from the design equations. Since it is a CHTR reactors, from the CHTR design equations, red equation in our last class also we have discussed. So, this is the material balance equations. So, here if other component tau, A, activation energy R, all components are known, only temperature if we vary 532 to 625, then corresponding x value will be vary according to this. So, when 535 was the reactor temperature, then corresponding conversion should be this. When this reactor temperature is this, then conversion should be this. This way we have discussed in our last class too. Similarly, for energy balance equations also, this was the energy balance equations if all components are known except this. Okay. So, this way similarly if we vary the these temperatures, first we said 535, then XCB would be 0. Okay. Since T0 is 535, that is why it is 0. If T0 is 535, then it would be 0. Okay. So, like that if we increase gradually like this way, then XC conversions from the energy balance equations will get like this. So, if we plot them, then this type of plot will come, that also we have discussed in your last class. This is the energy balance lines and this is the this is material balance lines and this is energy balance lines. Okay. Energy balance and this is material balance lines, both are crossings at this particular point, this is called steady state. Okay. So, steady state temperature. So, at that point where material balance lines and energy balance lines will cross, that is called steady state points. Okay. So, this line has started from here, this energy balance lines. In the energy balance equations you can see there are these are the components is there, these are the components is there. This is the T0 is called inlet temperature, feed inlet temperature, means this is the reactors. Here at T0 the reactant that would be charged inside of the reactor, and UA Fn or Fn is the molar flow rate, this is the coolant temperatures. So, either if these are the components, if we vary, these lines will change its nature, means these are the component value would change accordingly. So, then here these lines, if we changes one or two parameters for that particular system, so then the energy balance lines will be shifted like this. Materials balance lines is this, let us say here also it was like that, same it is remain like that. So, if we change the energy balance one parameter slightly, then energy balance lines would be like this. So, here was one dot, here was 3 dots. So, these are also called steady state, these are also called steady state, these are also steady state. Okay. So, if one parameter if we change in the energy balance equation slightly changing, so then material energy balance lines will shift it and will path follow this line. So, then number of steady state would be different. So, that is called, so here one steady state, here multiple steady state, therefore, we are discussing multiple steady states. Okay. So, if we change one parameter slightly, means whenever we are conducting any reactions, then means during operations one parameter we need to change due to the maintenance other parameters or the systems means operations. So, then what would affect in the other way, means energy balance lines or material balance lines that would also suffer or affect overall, then steady state point also will change. So, now this is the energy balance equations, that way we have written. So, this multiple steady state, material balance we are not considering, only energy balance equations that we already have discussed in your previous class too, that we can express in terms of kappa and Tc. This way energy balance equations we can write what is Tc and what is kappa, that we know. Okay. These are just parameters to make it simple, equation 1 energy balance equation. Now, from the design equations of a CSTR, this is the design equation for a CSTR, x equals to minus Ra into V by Fa naught, that is the design equation for a CSTR reactor. So, if these components, if we substitute in this equation energy balance equations, the equations once we can write this, means equation 1 and 2 both are same, but only x we are substituting with respect to the minor design equations of CSTR, minus RAV by Fa naught. Okay. Both are same, but here conversions we are eliminating, in place of that rate of the reactions volume and Fa naught, that way you are expressing, both are equations same. Okay. So, now this is the left hand side part, this is the right hand side part of the energy balance equations. Okay. So, this is the energy balance equations and this is the energy balance equations, conversions we are expressing or substituting with respect to this. Okay. This is the energy balance equation. So, now in the left hand side whatever, that is called heat generation terms. Okay. And this right hand side, that is called heat removal terms. Okay. So, whatever the right hand terms, that is called heat removal terms, and left hand side whatever, that is called heat generation terms. So, heat generation terms we can write this, means now the energy balance equations we split it up into two components. So, one is the heat generations, another one is the heat removal. So, if let us say heat generations equals to let us say 100, heat removal equals to 100. So, heat generate, from where heat would be generated, when there is a reactions, then once reactions is taking place, maybe exothermic or endothermic, depending upon that, heat generation should be there. If it is exothermic reactions, then heat generation would be there, since these are the rate means reactions. Okay. So, it is coming from rate, means reactions, heat of reactions, that would also come from reactions. Okay. So, heat generations each, let us say if we put all components, then it is coming 100, and heat removal, that is coming 100. So, here we can say heat removal equals to heat generations, both are same. So, if this removal terms is coming this Ta, Tc, Ta, okay. So, or Ua also we can say Tc means kappa Tc, that is the heat removal terms, that is due to the coolant that is circulating outside of the reactors. So, heat generation equals to heat removal may be or may not be. This Gt may be RT or may be Gt greater than RT or may be Gt less than RT. These are the way we can write, we can consider, means the amount of heat generated, heat removal may be equal or may not be equal, either one may be higher. So, if it is equal, then this steady state would come, that is the cross, means this steady state, this steady state, this steady state, means the amount of the heat generated during reactions, the same amount of the energy we are taking out, means system is steady state. Okay. And other than any point inside of this curve, that would be unsteady state point. Okay. And whenever we operate in a reactor, that should be a steady state. Okay. So, that steady state may be at this steady state we can operate, this steady state or this steady state, either ones, any one steady state we can set. Okay. If we set one steady state and if we change any parameters for that reactions, so then what would happen? So, overall energy balance lines will shift and heat generations will disturb. So, this is under steady state. If we change one parameter value, okay. So, let us say heat generations and removals, here if we means make a table with respect to the temperatures. So, by considering this, so heat generation and temperatures, this type of curve may come. Okay. And RT against temperatures if we plot using this, so this temperature and this RT, so how they will vary. So, this type of curve also will come. Okay. So, RT against if we plot T, so the lines would be like this. Okay. This is RT line, and if we plot Gt against temperatures, it would be like this. Okay. So, heat removal and heat generations. So, now two components we have, heat removal and heat generation. Now, individual components will consider and then that will discuss. First, heat removal terms. Heat removal terms is the RT. So, here heat removal terms, this is the heat removal terms equation, Cp naught into 1 plus kappa into T minus Tc. Tc is the this. So, this is the Tc directly proportional or that is related with feed inlet temperatures. So, T0 is the feed inlet temperature. So, I said the feed inlet temperature, suppose a system is running a particular feed inlet temperature we have started or operated. Certainly, if we change the feed inlet temperature, we let us say 100 to 150 we have done feed inlet temperature, the feed entering inside of the reactor. So, then heat removal terms will be different, Tc will be changes, T0 is different, then Tc will change. Once Tc will change, then this RT will different. So, let us say we have started at these temperatures, then heat removal terms equations would be like this, and so once changes the feed inlet temperature T01 to T02, these lines will be shifted like this. Similarly, if we change further, increase the feed inlet temperatures into T03, this RT, that is the heat removal lines, that would shifted here. So, means if we increase the T0 temperature, that T0 means feed inlet temperature, then the equation shifted towards right. If we decrease the feed inlet temperatures, so let us say reactions we have conducted at 150, started the reactions feed entering at 150 degrees centigrade, suddenly we decreasing the feed inlet temperature into 150 to 100 degrees centigrade, then these lines will shift this way. Okay. So, it would affect overall how both heat removal and heat generations both will plot simultaneously. Okay. Similarly, heat removal two parameters I said, one is feed inlet temperature, another one is kappa. This kappa also we can vary. Okay. So, how kappa increase or decrease? Fa naught A means Fa naught is the reactant molar flow rate and A is the heat transfer area. So, if molar flow rate if we increase, kappa will decrease, If molar flow rate decrease, then kappa will increase. If kappa increase or decrease, then this removal terms also will RT will change. So, RT depends on kappa as well as TC. TC depends on T0, means Kc TC depends on T0 and kappa Fa naught, let us say. So, if we vary molar flow rate of that reactant, then RT value will different. Okay. So, here's x axis, y axis RT. So, if kappa value is, let us say kappa when it would be 0, okay. When let us say this Fa naught molar flow rate is very low, means that feed we are entering at very low flow rate close to 0, Fa naught is very high, let us say Fa naught is very high, then K value close to 0. So, then this it would follow these lines, heat removal lines, okay. And if kappa value is gradually high, means when Fa naught is gradually decreasing, if Fa naught decreasing, kappa value will increase, then these lines gradually shift to this, means if Fa naught value, that is the feed entering inside of the reactor very low value. So, then very low Fa naught close to 0, then kappa value would be infinite, okay. This kappa value will be infinite, then though these lines will follow this. So, heat removal lines will follow this. So, it depends on kappa also, means that way we can increase or decrease. So, this way kappa value will increase or decrease, means molar flow rates of reactant mixtures. Now, this feed temperature remain the same, that we are not touching. So, only kappa value we are changing by changing molar flow rate, either increasing or decreasing. Okay, that way only one parameters, means feed inlet temperature was one parameter, and now feed molar flow rates that we are fluctuating. So, in that way heat removal lines also shift this way. Okay. Now, heat generation terms. So, heat removal terms is over. Now, heat generation terms. So, this was the heat generations terms or equations that we have discussed just this is the heat generation terms. Okay. So, this heat generation terms we can write minus delta H R x 0 heat of reactions into tau k by 1 plus tau k, okay. And k equals to this rate constant, specific reactions rate, that is this, okay. So, means actual this equation was this, here x equals to this for the first order reactions, we can write this, we can substitute it here, and then it would become this, and k also we can substitute here. So, then GT equations in terms of GT as a function of temperature we can write, okay. GT is the heat generations during reactions inside of the reactor, that is a function of temperature, we have written this way. So, if we fluctuate or change the temperature inside of the reactor temperature, so then GT value would be different. So, either this way you can write, okay, or this way you can write. So, or these equations we can write this way, okay. So, now GT value this way we have written. So, here's at very low temperatures, let us say reactions we are conducting at very low temperature, these terms we can eliminate, okay. This part we can neglect, or second terms in the denominator we can neglect. So, then these equations we can write this way, means GT equals to, means when at very low temperatures these equations we can write, and when very high temperature we conducting the reaction, the second terms would be dominated, this part, okay. Means when low temperature this part we can neglect, and so when high temperature we are conducting the reaction, this part would be dominated, okay. So, once this part is dominated, so then heat generations we can write this way. So, when the reactions we are conducting at high temperature or low temperature, depending upon that heat generations, this way you can write, okay. So, once we plot GT value against T, so high temperatures when we conducting the reactions, I said it would be like this. So, here 1 by 1 temperature, other parameter if it is known, then if we change this T, let us say 0 to let us say 200, any temperature, that may be degree centigrade, let us say, or Kelvin. So, if we change, so then GT value would be like this. So, it would follow this line. If high activation energy is there, means reactions we are conducting, the reactions having high activation energy, in that case these equations will follow, I said. So, at very high activation energy, so high temperature, so these equations will follow. So, then the lines would follow like this, means this is the heat generation terms, or heat generation lines will follow this path. Okay. So, either this or this, any ones may be. So, depending upon that activation energy for that reactions, means reactions operating, if it is low activation energy, so then reactions will be conducted at low temperature. If it is reactions is high activation energy is required, so then high temperature we have to conduct the reactions, and then the heat generation terms would follow this for high, and for low activation energy the reactions will follow this. Okay. So, now means here means the activation energy or high temperature, low temperature of the reactions, this we have considered. Now, if we change the space time, or space time means volume by volumetric flow rates. So, in these equations here, this is here tau was there, tau equals to V by V naught, V naught is the volumetric flow rate. If we change volumetric flow rate low, then tau will increase, space time will increase. So, then if V is decreasing, V naught that is decreasing, then tau value will increase. If V naught is decreasing, tau value will increase. If tau value is increased, let us say at a particular tau value, means volume by volumetric flow rate, this is fixed, then heat generation terms or lines is following this. If tau value is increasing, how? Volumetric flow rate decrease. At the volumetric flow rate, feed is entering from the inlet of the reactors. If we decrease, then tau value will increase, then these lines will follow. Further, if we increase the decrease the volumetric flow rate, these lines will follow. Means if further again if we decrease the volumetric flow rates, that is the feed entering inside of the reactors, it would follow like this. So, either this or this or this, either ones for a particular systems. Okay. So, whence volumetric flow rate we are changing. So, either these lines may follow, or these lines, this line or this line, any one. Okay. So, this way we can fluctuate the volumetric flow rates, means I said heat generations and removal terms both are there, means whenever we are considering any reactions or reacting systems. So, there means heat generation should be there, at the same time heat removal should be there, both simultaneously will take place for a system. If we are able to take out more heat from the systems, if it is exothermic reactions, let us say if you are able to take out the heat, more heat, whatever the heat that is generated inside of the reactors, if you are able to remove with the changing the flow rate of the coolants, then the temperature, the amount of the heat generated inside of the reactor, that would be down. Heat generation, that would be means amount remain the same. So, but if means heat generations and heat removal, means both simultaneously will take place, means operations, means due to the reaction, since the reactions is conducted. So, then heat generation should be there, and with the controlling heat removal components or parameters, we decrease or change the heat removal, means heat removal we can increase or decrease, that depends. So, if both are same, so then these are the way steady state concept is coming on steady state we can consider. Okay. So, means heat removal and heat generations, that is very crucial for this particulars any CSTR reactors when we are going to design, and there's heat exchanger is there. So, how to controls for a systems to get a particular steady state that we can operate. Okay. So, this way we can think about that. So, here the main components, what are the component or equations that is very useful. So, that these the material balance equations and this energy balance equations very important, and once we express in terms of kappa and Tc, the energy balance or these equations would become like this. Here we are These energy balance lines we are divided into two components, heat generations and heat removal components, and then individual temperatures if we component gradually able to know or vary, then GT value also will vary, and this heat removal lines and heat generation lines this is, and heat removal lines is this, both simultaneously GT and RT if we plot in a same graph. So, it would be like this for heat generations and heat removals would be like this RT curve this, and this is GT curve. Okay. So, now detail about, and see here these are the points would come that are called steady state points. So, here multiple steady state has come. So, if we start this way, so then only one steady state would come. So, other steady state in between this steady state we can eliminate, and the reactions would be shifted here, and at this particular temperature reactions may operate or we can conduct the reactions. Okay. So, this way we can think about that heat removal terms, heat generation terms for a particular reaction systems or reactions. Okay. Thank you. So, today is up to this.